Okay, question 11. We have two flasks with an ideal gas in them, the same ideal gas, and they're connected, so the pressure has to be the same. So let's write down the ideal gas law in the form of PV equals NKT. Now we have sort of two situations, situation P and Q, so I'm just going to label those. The pressure has to be the same, so we can write two expressions for the pressure, put those two equal to each other, and then we can start cancelling out. K cancels out. You can see that the volumes, P's volume is 2 of Q's volume, etc. And the temperatures in a ratio 1 to 2. And then that allows us to find the ratio of the number of particles, NP to NQ, which is going to be 4. And that is going to be the same as the ratio of the masses of the particles, because we have the same gas, so that the amount of mass is directly proportional to the number of particles in the gas. So the ratio of the number of particles has to be the ratio of the masses. So yeah, so this is going to be equal to MP over MQ as well. So the answer is C. And this is a typical ideal gas equation problem. Okay, the next one is simple harmonic motion. We know that the defining equation for simple harmonic motion is that the acceleration is directly proportional and opposite to the displacement. So that's just something you have to know. And the speed is always a maximum when you have zero displacement, and the acceleration is always opposite to the displacement. So D was the right answer. Okay, so question 13, we have a traveling wave moving through a medium and the graph shows us the wave at a given instant, the variation with distance of the displacement. We're given the frequency and the speed and what is correct for this wave. So definitely they're not in, X and Y are not in phase. They are actually in, they're completely out of phase, as we say. When X is up, Y is down, okay? The velocity of the particle at X is definitely not a maximum, it's 0, because the particle at X is performing simple harmonic motion going up and down, so it's going to have 0 speed at X. What about the horizontal distance between X and Z? Well, let's try and work out the wavelength, and we do that by the wave equation, V over F, 100 over 25, and that's 4 meters. And we can see that, okay, that means that X to Y is half a wavelength, Y to Z is a quarter of a wavelength. So yes, we are going to get a distance from X to Z as 3 meters. That's the correct answer, and therefore the velocity of the particle at Y is not 100 meters per second. That's the speed of the wave. Okay, question 14 is on interference, double slit interference, and we can use the formula S. The separation of the fringes is lambda d over d. Big D is the distance to the screen. We're assuming that's quite large compared to little d, the distance between the slits. And we're also looking at small angles, by the way. But yeah, we can use this formula, and if the distance to the screen is doubled and if the separation of the slits is also doubled, then D and D, both D's double, and then of course the slit separation is unchanged. The fringe separation is unchanged, so you get a B. So that's pretty straightforward use of this formula. And SL students, they really, whenever you are working with double slit interference patterns, then you should be very aware of this formula that is in your data booklet. So yeah, this is an interference question. Okay, next question, polarization, also topic 4, relatively straightforward. We have two filters, and initially the transmission axes are parallel, so you get maximum intensity, but then as you turn one of the polarizers through an angle theta, then we know of course that if you turn it 90 degrees you block the light completely, turn 180, you get maximum intensity again, and then you have to turn another 180 and another 180 to get maximum intensity transmission. So C is the correct answer. Okay, next question. Standing waves in a pipe that's open at both ends, and you really have to be comfortable drawing out the pipes and the standing waves in those pipes. Here we have the first harmonic in this situation with a node in the middle and two antinodes on either end. So you can see already here B has to be wrong because we have an odd number when we add them together. So A might be right, but let's just try, say, and draw the next harmonic. And the second harmonic, what does that look like? Well, then we have two nodes on like this, and we always have antinodes, of course, at the open ends, but now we can sort of squeeze in another half a wavelength, and so we don't always have a central node, we don't always have a central antinode, but it does look like the sum of the number of nodes plus the number of antinodes is always an odd number, and that is correct. Okay, so we move into topic 5 now. Question 17, we have a negatively charged particle in a gravitational field in position midway between two charged conducting plates. Okay, so it's in a gravitational field, it's at rest, so we can draw the free body diagram. Gravity down, there's an electric force pointing up. It's at rest, so they have to be balanced down. And what will cause the particle to accelerate? Well, we can see definitely decreasing the charge means that the electric force decreases, so that gravity is a bit stronger, so it starts accelerating downwards. So this is a question about the electric field between two metal plates, really. It's also about free body diagrams. Okay, we have a thin copper wire and a thick copper wire connected in series. We have a current flowing through them, and we have to see which quantity will be greater in the thin wire. Okay, so the current is going to be the same for two objects in series, so it's not A. And these two wires are made of the same material, so they have the same number of free charge carriers per unit volume. We label that with N in this. Remember, we have a current formula, I equals NQAV in the data booklet. So the N is the number of charge carriers per unit volume, and it depends on the properties of the material. Okay, then net number of charge carriers crossing a section of the wire every second, that's the same as the current, so it has to be D. That changes, and yes, as the area goes up, the drift speed goes down. So in the thin wire, we'll have the faster drift speed. Okay, simple circuits. Let's add the resistors in series to get like 4 and 8. And we want to find the current in the bottom branch. We know there's 8 volts across the bottom branch, and we have a total resistance of 8. So it's very easy to find the current, just voltage over resistance. And we get that the current is 1 amp flowing through the lower branch there. Okay, question 20, still topic 5, magnetism. We just need to know that when we have the force on a wire with an electric current that's in a magnetic field, the direction is always perpendicular to the plane containing the current and the magnetic field. And that's simply something we have to know.